In this question, we're given some titration data, and we're asked for the volume of NaOH that will be required to reach the equivalence point. So it says a chemistry student weighs out 0.0795 grams of phosphoric acid, a triprotic acid, into a 250 milliliter volumetric flask and dilutes to the mark with distilled water. He plans to titrate the acid with 0.0900 molar NaOH solution, and it says calculate the volume of NaOH solution that the student will need to add to reach the final equivalence point. So this is something that's very similar to what you'll do in a lab experiment, although we won't exactly calculate the volume of NaOH. We will calculate the mass, the molar mass of the acid. But here, this is a really good question. So what we're doing is a titration. And in a titration, if we know the amount, the moles of one reactant, we can find the moles of another because we use an indicator that'll change color at the final equivalence point. That's generally how it's done. So since we're doing stoichiometry here, we need to start with a balanced chemical equation. And the first reactant is phosphoric acid. So H3PO4 aqueous. And it's reacting with sodium hydroxide, NaOH, which is also aqueous. And remember that an acid-base reaction is very similar to a double displacement reaction. In fact, it's a type of double displacement reaction where H goes with OH to form water and Na goes with PO4 to form the salt. So to find the formula of the salt, we have Na plus PO4 3 minus, cross our charges, and we get Na3PO4, which is aqueous. And then finally, we get H and OH, which makes water. And water is a liquid, so we form something that's not aqueous, so that's the driving force of the reaction. Now we need to balance it. Well, I noticed that to make Na3PO4, I need 3 sodiums, so I'm going to put 3 in front of NaOH. If I have 3 H's and 3 OH's, I will make 3 HOH's, or more commonly written as waters. So H goes with OH to form water. If I have 3 H's and 3 OH's, I will make 3 waters. We now have a balanced chemical equation. Now that we have a balanced chemical equation, let's go to a plan of attack. Well, if you notice here, I'm given a mass of phosphoric acid, and I'm asked for the volume of NaOH that I'll need. So I want to start with grams of H3PO4, which I want to convert to moles of H3PO4. Once I have moles of H3PO4, I want to convert to moles of NaOH. And remember, because this is a titration, so we're going to monitor the equivalence point with some kind of indicator, this is possible. Said another way, I can figure out some information about one reactant from another. This is not normal. Normally we go from reactants to products, or sometimes products to reactants, but we don't usually go from reactant to reactant, which we are doing here. Moles of this reactant to moles of another reactant, and that's what makes a titration unique. Finally, once I have moles of NaOH, I can find liters of NaOH solution. So this is my plan of attack. So grams to moles, we've done this many times before. So we have 1 mole of H3PO4 is equal to the molar mass of H3PO4, which is 98.00 grams of H3PO4. And we found that by adding up 3 hydrogens of phosphorus and 4 oxygens, their molar masses on the periodic table. Next, we want to go from moles of H3PO4 to moles of NaOH. Well, if we look at the balanced chemical equation, for every 1 mole of H3PO4, that's equal to 3 moles of NaOH from the balanced chemical equation. One of these reacts with 3 of these, so these are equal. And then finally, we want to convert from moles of NaOH to liters of NaOH solution. And to do that, we need to use the molarity. This is 0.0900 moles per liter. So 0.0900 moles of NaOH equals 1 liter of the NaOH solution. So these are all the equalities that we're going to need to do these conversions. So now starting with 0.0795 grams of H3PO4 times, in the first equality, we want grams of H3PO4 to cancel out, so we put the molar mass on the bottom, 98.00 grams of H3PO4. And on top, we put 1 mole of H3PO4, phosphoric acid. In the next conversion, we want to go from moles of H3PO4 to moles of NaOH. Well, we want moles of phosphoric acid to cancel out, so we put 1 mole of H3PO4 on the bottom from the balanced chemical equation, and 3 moles from the balanced chemical equation of NaOH on the top. Finally, for the last conversion, we want moles of NaOH to cancel out, so we put the molarity number of moles, in this case 0.0900 moles of NaOH on the bottom, and on top we put 1 liter of NaOH solution. Multiply by the top, divide by the bottom, multiply by the top, divide by the bottom, so on and so forth. And I'm just going to shift this up a little bit and write the answer down here. What you find out is you get 0.027048 liters. However, in a titration, we will often convert this volume into milliliters, so we're going to multiply it by 1,000, and we're also going to convert our sig figs at the same time. We have 3 significant figures here and 3 here, so therefore we want 3 significant figures. So we want to basically multiply by this by 1,000, so move the decimal place 3 times, and 3 significant figures is this one, so we end up with 27.0 milliliters as our final answer.